We've talked about now how if you take a plane wave and the plane wave arrives at some aperture, the wave that passes through that aperture will no longer be a plane wave. If it's no longer a plane wave, then it must have some transverse structure in the x or y direction, if propagation's in z. And if we take the Fourier transform of that transverse structure at the aperture, in other words, we take the Fourier transform of the aperture itself, then we find the far-field diffraction pattern. In other words, if we want to know the far-field diffraction pattern, we have a machine that does it for us. It's the Fourier transform. The far field, though, can be a very long way away. Technically, you don't reach the far field until you get to infinity. So is there anything that can bring infinity a little bit closer? Is there anything that can transform the angle of a wave into a position? What about a lens? So here's a situation we have. We've got waves propagating. They've over here off the screen, we've had some diffraction event, and now waves with different transverse k vectors, which means we have different angles theta, we're propagating towards a lens. Well, all of the rays with a particular angle theta will be mapped to a focal point, a distance h dashed away from the optical axis. And the distance h here, h dash, can be found using the focal length of the lens. So the lens, in other words, takes waves with a particular angle and focuses them to a single point on the other side of the lens, the focal distance away. This result comes out of the lens equations you may have seen in other courses. For small angles, we have this equation here that the angle theta is given by h dashed on f. In other words, we can write the height h dashed as being the product of theta and f. So now we have a way of mapping the angle theta to a position in the focal plane, which is why the focal plane of the lens is sometimes also called the Fourier plane. So the lens maps all plane waves at angle theta to a point at distance h dash from the optical axis. In other words, the lens maps plane waves with transverse k vectors, kx and ky, to a particular point x dashed and y dashed at the focal plane of the lens. Because the transverse k vectors, kx and ky, are linearly related to angles, theta x and theta y, we have a mapping now between the transverse k vectors and points at the focal plane or the Fourier plane of the lens. So the field amplitude at the focal plane of the lens is the Fourier transform of the aperture through which the plane wave originally propagated. That's a really useful result. Now we're going to take the last two concepts we've dealt with, that is diffraction and lenses, and merge them together to make an analog Fourier computer. So let's start with the diffraction part. So just as a reminder, diffraction means we have some plane wave. We're dealing with plane waves here. It could be some other sort of wave, but we're only assuming we have a plane wave, otherwise things get a bit more complicated. So a plane wave arriving at some slit or aperture. And the plane wave has no components in the kx or ky directions, only in the kz direction of propagation. But after being modified by this aperture, we will have components in the kx and ky direction, resulting in the wave spreading out. And there'll be waves traveling in directions theta x and theta y that are not zero, and these angles depend on kx and ky in this way. And then if you go a long way away from this aperture, the amplitude of the field that you see will be proportional to the Fourier transform of this shape of the aperture here. So that was diffraction. And so let's imagine we have waves coming through this aperture now, and we get waves propagating with different angles, and the amount of wave propagating at any given angle will depend on the Fourier transform of this aperture. So some angles may have more wave, some angles will have less of a wave. And here I've represented three different angles, theta 1, 2, and 3, by different colours, but the colours play no significance. That's just to visually separate them. So that's the diffraction part. Now we're going to add the lens. And the lens takes these waves propagating at different angles and focuses them to particular spots at the focal plane of the lens. So the light travelling at angle theta 3 will be focused down here, theta 2 in the middle, and theta 1 at the top. So now we've taken light at a particular angle and converted it to a spot on the focal plane. And the strength of this spot, the amplitude of the field of this spot, will depend on how much of the wave was travelling at this angle, the amplitude of the wave component travelling at this angle. So each plane wave travelling at some angle theta x and theta y will be focused to a point, and the position of that point will be x dashed y dashed at ZF. So ZF is the focal plane, and x dashed y dashed are now the x and y coordinates at this plane. And the coordinates x dashed and y dashed will be given by the angle of the wave, here, the angle of the wave, multiplied by the focal length of the lens. And that'll be true for the x and y directions, and here ZF is, again, the focal plane. The angles can be written in terms of kx and ky. But remember, kx and ky can be computed as the Fourier transform of the aperture. And so therefore the amplitude at some point, x and y, will depend on the amplitude of the plane wave focused to that point, and the amplitude of the plane wave focused to that point depends on the Fourier transform of the aperture. So the focal plane of the lens with focal length f, we're going to call the Fourier plane. And at this plane, the amplitude of the field depends on the amplitude of the plane wave components focused to that point. The amplitude of the plane wave components at any given angle are found via the Fourier spectrum of the input wave, that is, the Fourier spectrum of the aperture through which this plane wave has passed. That is, the field at the points x dash y dash at the focal plane is going to be proportional to the Fourier transform of the wave that's passed through this aperture here. So in other words, what we've built is an analog Fourier computer. It's the lens that computes the Fourier transform of the input light. And so whatever field amplitude you have at the focal plane here, which we're calling now the Fourier plane, this amplitude is now proportional to the Fourier transform of this aperture. Noting that we have to think about now the complex amplitude of this field, not just the intensity, because the Fourier transform has real and imaginary parts, or an amplitude and a phase. And the amplitude and phase of the field here is crucial to the mechanics of the Fourier transform. So I want to finish this part of the course on Fourier methods by thinking about the diffraction pattern of a cat. So the experiment would be something like this. You take this image of a cat and you print it onto a transparency. You shine a plane wave through that transparency, and it'll be a plane wave with a single wavelength, so like a laser field, but a sheet of laser light, a plane wave. You shine that through this transparency. On the other side of the transparency, you would have a diffraction pattern. You collect that diffraction pattern with a lens and focus it down. At the focal plane of the lens, we have the Fourier plane, which will be the Fourier transform of this cat. Or in other words, this is what you would see. You would see the absolute square of the Fourier transform of this image. Why the absolute square? Because your eyes are only sensitive to the intensity of the field. That is something proportional to the number of photons. What we cannot see is that this field will also have a phase. You can imagine building some sort of interferometer to measure this phase. And of course the phase is important, because if you allow this field to propagate and re-image with the lens, you need this phase to reconstruct the image, but we cannot see the phase directly with our eyes. Now, one of the powerful things about Fourier transforms is if we modify this image in some particular way, we can anticipate what the Fourier transform will look like without doing any maths at all. So let's imagine we draw diagonal lines across this image. We have some diagonal modulation across this image, and we can imagine what the Fourier transform of these diagonal lines might be. It'll be a whole bunch of points like this along this diagonal direction. And so the Fourier transform of this modulated cat, this cat behind bars, will now look like this. And again, the phase is a bit of a mess, but we can anticipate at least what the magnitude of the Fourier transform will look like. And so I guess this is really kind of a good place to finish this part of the course with a take-home message or two. The first take-home message, and I think the most important one, the one I hope I've communicated through these videos, is that a key power of knowing what Fourier transforms look like is being able to understand how things work in an intuitive way without having to compute anything. So if you know what the Fourier transform of these lines is, you can anticipate what the Fourier transform of this cat might look like. If you know that the Fourier transform of a Gaussian is a Gaussian, then you can think about how different wave components might propagate under just dispersion, knowing that you have some spread in the k components. By knowing what the Fourier transform of a rectangular aperture is, you know what the pattern of light you might get behind that aperture would be without having to really compute anything. Just knowing in your head what these Fourier transform pairs are. And that's, that table of Fourier transform pairs is really a go-to reference to understanding a lot of things in this course. The other thing to bear in mind is that on the occasions where you do have to compute something to get a really quantitative answer, then computers are really good at computing, and computers are particularly good at computing Fourier transforms. There are lots of tools that enable you to do that. And so with that, I'll finish this part of the course.